Hello and welcome to my YouTube channel. This is programming using C++. My name is Siobhan Richards. I've worked as a front-end engineer for about 2 years, and I've taught computer programming concepts for a year as a professor. Okay, so you chose C++. C++ is a great first language. It's closer to hardware, right? It's usually used in microcontrollers, robotics, and so on. This is the master language, right? So it's good to start with C++ as your starting language. Okay. Well, the other languages you'll pick up easier if you start with C++. So let's dive in a little here. We have history of computers. So let's talk a little on the history. Discuss a little on the history of the computer and why are we programming today. Okay, so let's look at what is computer architecture here. Okay, you have this thing called the von Neumann architecture, and if you look at the flow here, we have inputs. These inputs could be typing on a keyboard, clicking of a mouse, or typing code into a source file. Then we have the central processing unit, which is composed of the control unit as well as the logic or the arithmetic logic unit. And then we have this memory layer, which is very important. And then we have the output. So the input, again, it could be sensors, typing on a keyboard, or video cam, right, webcam. You will take those inputs, you'll process the input, change it from whether it's analog or digital. You're changing it to digital, that it could be represented in memory as ones and zeros, right? So you store, let's say if it's a program, you store that program in memory as well as the data in memory, and then you could access it from memory again, process it some more, and then provide some output that matches your business logic, right? So this is the von Neumann machine. In these over here are the electrical components that matches this von Neumann flow here. This is like the motherboard, right? So these are all the different IOs, CPU, sockets, RAM, and so on needed, right? Memory slots, floppy disk, and so on. That's needed to conduct this von Neumann flow here, right? So why did we start with the von Neumann machine? Okay, before the von Neumann machine, computers used to be special purpose, meaning it's designed for a specific purpose. So for example, your calculator, it only does calculations, built-in functions there on your calculator. But after the von Neumann machine was invented, we basically decouple software from hardware. Before it used to come in pairs, right? So you used to have the software aligned with the underlying hardware. This decoupling of software from hardware gave rise to software development and hardware development. So there's two sides of the same coin, right? So just remember the von Neumann machine, this reprogrammable layer, that memory layer there, allows you to reprogram your computer, so you could upload different source codes and using the same hardware to do a different task. So now we have our desktop, mobile phones, laptops that have multiple different applications, right? You could have your Word document, video recorder on there, and it's the same underlying hardware. Why is this good? Well, you'd have to be building separate computers for separate tasks, right? So this decoupling allows for multiple software, same underlying software. So just for you to imagine, just imagine this. There are way more software applications than computer models or manufacturers, right? So that software side is exponential growth, while the hardware is kind of slower in that sense. And it's better because then developing hardware is harder than developing software, which is just a bunch of files. Okay, so that's the beauty of the von Neumann machine. Okay, all right. So what is software, right? Software for a computer is written using a programming language. In our case, it's going to be C++, We transform that programming language in the source code is transformed into binary codes, right? Binary code, ones and zeros are machine code. This machine code feeds the underlying hardware, ones and zeros, to do the bit shifting and bit manipulation so that we could have this output data on our system. Just to note, if we dive a little deeper here, the hardware layer is based on electrical engineering theories, okay? And this is combinational and sequential circuits, right? Ones and zeros, logic gates, right? So these are the electrical components needed to do the bit manipulation on the lowest level layer of your computing system. Okay, so what's our job as a software engineer? Basically, for example, let's say you're going to write your first C++ code. You have standard out, hello world, right? So software developer want to print hello world. They'll create a source code, a .cpp file, hello.cpp. You'll have your pre-processing, pound include, IO stream, whatever library you need. You'll have your compilation, right? So it compiles the source code into assembly code. So .object files. Then the assembly code is broken down into binary machine code. And then you have your linker that links all your different libraries together, and you'll have your executable at the end, which are apps, right? Which are apps. So most apps are .exe files, right? Executable on your system. So what is programming? Programming is writing code in a specific language, right? For some desired output that matches your business logic, right? So it has to be aligned with whatever desired output you need. Maybe it's a predictive task or classification task or parsing or something, right? Modification task, okay? So what determines well-written code? First, we have to know that C++ uses camel case, right? So it's a camel case when you create your variable names, function names, methods names, packages, and so on. Your code has to be readable and understandable. So variable names have to have meaningful variable names. Consistent formatting, you have to follow indentation, right? And scoping, which we'll look at later. It has to be modular, right? You could have different modules set aside for a specific function in your business logic, right? Your desired output that you're trying to find. Meaningful names, do not repeat yourself. Minimal complexity, should be well tested. You have to have your unit tests, make sure each function does what it do, and maybe later you do end-to-end, make sure all the different layers work. And then you have some version control, which is you have GitHub Perforce, right? So these are tracking tools used to keep track of your productivity, right? Of your commits that you make on your source code, like how what are the different changes that you've modified on your code, and you could revert back to these different changes and so on. And you should follow solid principles. So this is what constitutes a well-written code, right? So these are good conventions to use when thinking of well-written code. The other thing that you should know as a software developer or coder is the software development lifecycle. So if you've taken a business class, these lifecycle methods are typically used to describe the stages in a business or a product. And we've taken those lifecycle methods and applied it to software. So we're viewing the software, the overall software, as a product in itself. Okay. So this lifecycle, we have waterfall versus agile software development. So for agile, you have planning, defining, design, testing, deploying the software. And this is an iterative process. Meaning it's a feedback loop. So you could have some initial design for your software. You could put it out into the market and then just see how the user react to it and what improvements you could make with the agile process. And then you could keep doing that improvement, plan a new layer or feature, and keep deploying it to the market and doing this rapid testing type of process. So you could gather feedback as fast as possible, so you could have the well-tailored product each iteration, right? So each iteration you're getting better and better. Waterfall, on the other hand, is more of a linear process. So you gather all your requirements first. So what does your customer need or stakeholder need? You conduct all your designs, UML diagrams, CRCs, sequence diagrams, and so on. You do your implementation, so you start designing your source code. You do your testing, maintenance, right, and so on. But there's cases, right? So typically the main approach is agile, right? So agile software development, agile developer. But there are cases where waterfall is better. For example, safety critical cases. You want to make sure that the software is working according to plan, right? You don't want to go to the next step since it's safety critical without making sure that everything is considered in the initial stages above. Okay, so that's waterfall versus agile development. You also have other different lifecycle methods like spiral and so on, but these are the two main clashing approach. Okay, clashing approach. Next thing you need to know as a software developer or a coder is development tools, right? So how are you going to create these software without tools, right? So it's like a mechanic, you need different tools to do your job, right? The first tool you need is a IDE. This is a integrated development environment, right? So for you have Eclipse as an IDE, and this is for source code editing. You have VS Code. I like VS Code. PyCharm, Sublime. So these are editing software for software for writing software. Okay. However, you could use a notepad, right? You could use all these different text editors because it's really that, right? You could even write software in Word, but it's not optimized for your job, right? So these integrated development environment helps, right? You could have different plugins and all these goodies that help you to be more productive as a software engineer. So you may have plugins that help with syntax. You have linting tools, code completion tools like GitHub Copilot, and so on. So these IDEs make development easier, right, for the modern engineer. The other thing that you need is a scripting language. You need to know some scripting language. Here I'm introducing Git Bash, right? Because with the Git Bash, you could easily upload different commits or different messages on your code, on your source code, to the cloud, right? To the Git repository that you create. But the Bash is, so just remember from the von Neumann machine, we have this hardware layer, right? And we have this kernel, right? So this kernel sits on top of the hardware layer. But in software, right, we have application software and system software. The system software is your operating system, and your operating system contains the kernel, right? So rather than using a graphical user interface, which is common for Windows machine, right, you click, let's say you want to create a file, you click new file, you have to click through and create a file. You could get to that kernel layer, which controls the hardware, from the system level, all right? So from the command line, which is a shell, right? So you need your born again shell or any other shell, maybe a TCH shell or a corn shell. You could use this shell to have more control over the kernel, which sits right on top of the hardware. So that's why you need to know some scripting language. And what are some commands you may need? System level commands, file manipulation, processes. Maybe you need to do some cron job or something. So all of these commands are system level commands. They sit right on top of the hardware, and it's more on the lower portion there. Okay, so you need to know some scripting language, right? So how to make a file with a script, make there and CDs and so on, right? So maybe from your application, you may request to use those commands, those system commands, to make your application run more efficiently and to manage, have more control over the processes running on your device, right, or your machine. Okay, so that's shell, right? So once you have those, we could get started with C++. Okay. So we have this VS Code. You could click on this one here, but let's just talk a little more on C++. So it's a compiled language. So it's generally translated into machine language, right, that is understood directly by the system, making the generated program highly efficient, right? So you have a compiler and a linker. Okay, it's very scalable, object-oriented language, perfect for large-scale application, and it provides low-level direct memory management. So that's really why you use C++ for robotics and so on. It's more efficient in terms of memory management, right? So it's a statically typed language, which gives you more control over managing memory. You could allocate memory here, deallocate here, so it's more control over the memory. Just keep in mind, with programming, you have two main types of errors. Okay, so you have syntax errors, which are structural issues with your code. So like a subject-verb agreement in English, right? So can this token follow this token in the code, right? And then you have semantic errors, which requires debugging, right? So debugging means you have some bug and you have to debug to figure out what the issue is. So semantic errors are typically harder to catch than syntax errors, because semantics, it's the meaning, right? You may misunderstand the business logic necessary there, and you could write the code, it runs, but there are bugs in the code. It's not as efficient as it's supposed to be, or you may make a mistaken calculation or something. Okay, so that's the two general types of errors. And just remember, semantic errors are very harder. This is where a lot of software engineer is working on all the time. Semantics, like did I do the best? Did I use the best meaning? Did I use the best algorithm here? Or why is my code running and this is not working here, right? So that's semantic errors, okay? So let's go into these different layers, peeling off the onion of the C++ programming language here. All right, so the first thing you need to know is reserve words. So in C++, there are at least 95 keywords, reserved keywords. So these are keywords set aside by the language that you can't use as variable or function names. So these are set aside by the language for some specific underlying semantic or meaning in the language, okay? All right, so keyword example, you have auto, break, case, char, const, continue, delete, do, double, float, and so on, okay? You have mutable, namespace, template, throw. So it's a lot of keywords, okay? This is a couple here. All right, so just again, keywords, they have special meaning within the programming language. So it cannot be used as identifiers, variable names, function names, and so on. So they have some specific functionality in the language. Okay, so the other thing you have to know, again, before we start to do some hands-on, is block indentation, right? So function scope, right? So how do we scope function or variable scoping? How do we scope access in our code? So what do I mean by scope? So you have global scope versus local scope. Do I want this variable to be seen by all these different functions and classes, or do I want it to stay locally within the function? So once you understand scoping, and it's typically used in functions, right? You'll be able to know how you want to structure your code, if you want this variable to be seen by the other functions or not, right? So maybe it's a temporary variable, you just have it inside a function, okay? And the next thing about scoping is that C++ uses semicolon, right? So after each line, you need a semicolon to end your statement, and you use a curly brace. Curly braces does the scoping. So here, for example, in the main function, you see curly braces. That's the scope of the main function, right? So scoping is very important. When you're writing a lot of code, you have to scope your variables correctly, okay? Otherwise, you may have overwrites and so on, okay? All right, so let's start with data types. First thing we need to know before writing a code, or we're going to write code on this one, is data types in C++. So you have fundamental data types. Just remember, C++ is a statically typed language. What do I mean by that? You have to directly tell the compiler what the data type is, right? So if it's an integer, you have to say int. If it's a string, you have to say it's a string. If it's a float, you have to say it's a float. If it's a double, you have to say it's a double. So there are two main data types here. We have at least seven fundamental data types, and then we have about 3 user-defined types. So the fundamental data types are those, again, remember with keywords, they are set aside in the language. These are specific data types, and it represents a certain allocation of memory in the language. So these 7 are the building blocks of all the different data types, right? So if you have these user-defined data types, for example, a class, it's made up of these primitive or the fundamental types in the C++. So your class will have some maybe int or string or something built in to the user-defined type. Okay. So again, 2 main categories. We have this fundamental versus user-defined. In other languages, it's primitive versus reference. Okay. So what are built-in types? So these are involved in handling and storing and processing processing data for desired input. Okay, for desired output. So you give it some input. So this input could represent an integer, it could represent a float, it could represent a string, and then you need some desired output. Maybe it's a multiplication task, maybe it's a parsing task or something. Okay. Right, so these are kind of like building blocks, data structures in the language, those small level, low level data structures in the language. All right, so for fundamental types, you have 6 main fundamental types. You have integer types, right? You have signed integer, unsigned integer, floating types, Boolean types, and void types. So these are all the fundamental data types in C++. Okay, so now we're with our next video, we'll go through declaring and initializing all these different fundamental data types in C++, all the different fundamental data types. Right, so I hope this makes some sense here. So we've gone through looking at computers, right, how they're made, right, so the architecture of the computer. We looked at data types in C++. We've looked at all the necessary tools you need to begin coding, and for our next video, we'll go through actually hands-on writing, declaring and initializing these data types, all the different data types in C++. And then from there, we'll move to operators. Okay, so we'll see how operators and data types work together. Okay, thank you for listening, and I hope I'm making some impact here. All right.